Well, as students, now today's lesson I have chosen as DeMorgan's laws, which is our next lesson as part 2 of Boolean algebra. So let's begin the Boolean algebra part 2 title DeMorgan's laws. In DeMorgan's laws, we are having two statements. Number one here, which is algebraically represented in the form of a mathematical relationship with two variables a and b. And here in the first we are having a relationship where we have in the left hand side complement of a plus b equal to product of complement of a and complement of b. And this is the first Boolean relation, Boolean law in the as per De Morgan's law, means it is nothing but the De Morgan's theorem, we can say in other words. What it states, this is the mathematical relationship, and what it states actually. Going through this very relationship, we can sum up it with the statement, with the quote that complement of sum of the variables is equal to the product of their complements. In simple and short and precise terms, we can state it as complement of sum is product of complements. Here this sum represents the OR operation, and this product or the dot represents AND operation. So in other terms, we can state this Boolean law as complement of OR operation is the AND operation of the complements of the variables. So sum can be termed as the OR gate operation and product as the AND gate operation. So this is the first case. Let us go for this first statement in terms of the logic gates symbol representation. Here I am having a gate which is a NOR gate. So with inputs A and B, what will be the output of this NOR gate? It will be complement of A plus B. As per this De Morgan's law, it is equal to product of the complements of the inputs. Means it can be represented in other gate circuit symbol representation where we are having A and B as their complements, and the complements of A and B are to be fed to an AND gate. So output will be the product of dot of A complement and B complement. Here this gate is receiving A complement, I have represented it with bubble over here, and B complement it is represented with bubble over here. So symbolic representation of this very De Morgan's law is over here with NOR gate for the left hand side, and this bubbled AND gate in the right hand side. Two bubbles at the input side represent we are feeding this AND gate with the complements of the inputs, A complement over here and B complement over here. So product will be the product result, or the output will be product of the inputs, complements, which are complement of A and complement of B. So next, De Morgan's law is about the product. It is over here represented algebraically with two variables A and B as complement of A dot B is equal to sum of complement of A and complement of B. What it means? It means that complement of the AND operation over the variables A and B is equal to OR operation performed on the complement of A and complement of B. So precise and in crisp terms, we can state it as complement of product is sum of complements. Remember, complement of product. Here it is. Complement of product is sum of complements. Clear? So in logic gate symbol representation, this very DeMorgan's theorem or the law can be represented as over here. For this left hand side, we are having complement of A dot B. So this is nothing but the product, or this is nothing but the output of an NAND gate. So this is NAND gate with two input A and B, and its output will be complement of A dot B. So for right hand side, it is represented over here with an OR gate, because we are having OR operation over here, so simply OR gate. But this OR gate is receiving the inputs A complement and B complement. So for A, I have put a bubble over here, so and another bubble over here for input B. It means this OR gate is receiving the inputs A complement and B complement, and the final result will be by the OR operation of this OR gate means sum, in terms of sum of its inputs A complement and B complement. So over here, this representation in terms of the logic gate symbols is for this DeMorgan's second law. Now going for the proof how it is equal, we are taking the help of the truth table. For this truth table, I am having the inputs A and B with all four possible combinations for these two inputs, and next column over here is generated for their complements. A complement separately over here, complement of A for 0 it will be 1, 0, 1, for 1 it is 0, for 1 it is 0 as well. And now for B, I have a column B complement. It will be the complement of this B for 0, 1, for 1, 0, accordingly as it is. Now another column is generated over here, A dot B. Now A dot B will be the inputs A and B to be multiplied and operation performed on the A as well as on B. So A dot B for this 0 0 combination will be 0, for 0 and 1 combination it will be 0, for 1 and 0 it will be 0, and for 1 dot 1 it will be 1. Now taking the complement of this A dot B complement. So over here complement of 0 will be 1, yes, accordingly 1, for this 0 as well 1, for this 1 it will be 0. Now I have got this complement of A dot B. Now another column is generated over here, which is sum of the complements of A and B. So complement of A is over here, its column is here, complement of B, its column is here. So we are going to add up these columns, and this column is generated. What will be the sum? 1 OR with OR. 1 plus 1 is 1, and 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. Okay, what we conclude over here from these two columns? See, observe, complement of A dot B is equal to sum of the complements of A and B. Isn't it same? So here we proved this very theorem. Complement of A dot B is sum of complements of A and complement of B. Now for another step, I am taking the column for A plus B. Likewise, we generated over here A dot B we are generating a column for a plus b separately. So inputs a and b are to be summed up, odd operation. A 0 plus 0 will be 0, and 0 plus 1 will be 1, 1 plus 0 will be 1, and 1 plus 1 will be 1 accordingly. Now take complement of this. Complement of this is, for 0 it is 1, 1 is 0, 1 is 0, and complement of 1 is 0 as well. Now what about a complement dot b complement? Means we are taking AND operation for these complements, separate individual complements of a and b. Now dot operation AND operation performed over here will give us the column 1 dot 1 is 1, 1 dot 0 is 0, 0 dot 1 is 0, and 0 dot 0 is 0. Now observe these two columns. These two columns. What we observe? These are same. For each input status, the columns indicate the same status at the output. Now here this truth table proves that the De Morgan's law is valid in Boolean algebra as well. So for the sake of the simple statements, you should remember De Morgan's law in crisp terms. For first, complement of a plus b equals to product of complements. Simply remember, complement of sum is product of complements, and for this, complement of a dot b is equal to sum of complements. Remember, in crisp terms, complement of product is sum of complements. Hope you got it. Thank you very much for today's lesson. Thanks for watching. Nice of you. Till next lesson. Assalamu alaikum. Bye.